So it's a pleasure to introduce Mark Gross today from the University of Cambridge, who will talk to us about intrinsic mirror symmetry.
Okay, well, thank you very much for the invitation. I feel a little bit like an imposter in giving this talk because I'm not actually in the Western Hemisphere. I'm a couple of miles to the east of the prime meridian, and hence in the Eastern Hemisphere. I was wondering whether there was a venue I could use slightly to the west of the line, but I think that would not be reasonable under the current circumstances. So I also see many names I don't recognize on the list. So I'm going to assume that the audience is broad enough to not be so familiar with mirror symmetry in general. So I'll begin with a little bit of history. Let me just first begin by saying I will be talking about joint work with Bernd Siebert, and it's primarily about a paper which was released in 2019 on the archive. So let me give a brief potted history of mirror symmetry, very brief. And this is really the only place where my talk makes contact with physics and string theory in particular. So the story starts roughly 1989 or 1990 with the observation by various physicists. There was a key paper of Candelas et al. And Green Plesser, who observed that Calabi-Yau threefolds tend to come in pairs. So let's say a Calabi-Yau X and another Calabi-Yau X check. And here by Calabi-Yau, for the moment, I mean a compact complex manifold there's some slightly interesting noise coming through.
Kind of scary, huh?
It's all in the mind.
Are we good together? Something seemed to have gone wrong. Andy, can you?
Yeah, you're good.
Okay. Okay, compact complex manifold with a nowhere vanishing top dimensional homomorphic form. And in the case of the Calabi-Yau threefolds, the key point was that there seemed to be this mysterious interchange of Hodge numbers, namely H11 of X was equal to H12 of X check and vice versa. H12 of X is H11 of X check. So this was the first thing that was noticed. And one of the key examples was the quintic threefold. And its mirror. So I need to go to new board. So let's take, for example, X to be the zero set of the polynomial x0 to the fifth plus dot 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 plus x 4 to the fifth that sits inside CP4. That's a non-singular hypersurface, a three-dimensional complex manifold. Let's see, I just got a question by chat. I'm going to not worry about H1 for the moment. So this is quite introductory. Okay, so there's a quintic threefold. And in this case, H11 of X is 1 and H12 of X is known to be 101 dimensional. And then we have the green cluster construction. Where you consider the group, so if you take the group Z5 to the 5th, acting on CP4, by multiplication by 5th roots of unity. So A0 through A4 in Z5 to the 5th acts on CP4 by a point with coordinate Z0 through Z4. Let me be consistent, X0 through X4. Goes to C to the A0 X0 through C to the A4 X4, where C is equal to e to the 2 pi I over 5 as a primitive 5th root of unity. And inside here, we have a subgroup. Let's call it G is Z4 to the 4th, sitting inside Z4 to the 5th, sorry, 5, via G is equal to the set of all tuples A0 through A4 in Z5 to the 5th, such that summation AI is equal to 0. So G also acts on CP4. And it's also obvious that G acts on X. In fact, so did this larger group, but we just care G acts on X. And then X mod G, well, if you divide out by this action of G on X, you get something very singular, but it has a resolution, has a Calabi-Yau resolution X hat to X mod G. So you can resolve the singularities and you get another Calabi-Yau. And the basic calculation that Green and Plesser did was that H11 of X check is equal to 101, sorry, and H12 of X check is equal to 1. So the Hodge numbers are interchanged. Okay, so that was the very first example. The next key step was a paper of Candelas, Stolosa, Green, and Parks. Who did a rather amazing calculation. I'm now getting used to being rather a bit on the older side, so when I talk to young people, they probably don't actually realize how amazing this was, but it really was a incredible, for those of us around at the time, it was really an incredible thing to come along. But what they said is one can calculate the numbers of rational curves on X by performing certain period integrals on X hat. So a period integral is something of the form integral over a 3 cycle of the holomorphic 3 form. Yes, sorry, I left off or not left off, I added an E there when I shouldn't have, yes. There are 2 different Greens involved in this story. So a period integral is something of the form integral of alpha, where alpha is a 3 cycle on X hat and omega X hat is nowhere vanishing homomorphic 3 form. Okay, so I'm not going to go through the details, but key point here is this question as to what the numbers of rational curves mean. So you can think of a rational curve rational curve should be thought of as a map, should be thought, at least to first approximation, as a map f from CP1 into X, representing some homology class, representing some homology class in beta in H2 of X Z. So the push forward of the fundamental class of CP1 under this map should represent the class beta. So i.e. f lower star of CP1 is equal to beta. Now, generally, of course, you can reparameterize the CP1, so you work modulo reparameterization. And then you count the number of such maps, mod reparameterization of the domain, mod automorphisms of the domain. Now, of course, those of you who are experts in this know that I've vastly oversimplified, but for the sake of this talk, I want to keep things at that level. So, for example, the number of lines in X is the number of maps F from CP1. By the way, these maps should all be holomorphic. From CP1 to X, representing the class of a line in H2 of X Z, which will be just a generator of this homology group. And in case you're interested, that number is 2,875. And these numbers get big quickly, and mathematicians didn't know very many of them. Maybe because Sheldon is here, I should also mention the number of conics, which was 609,250. This is Sheldon Katz, and that was, I think, the last calculation that really predated the advent of mirror symmetry. So it was quite surprising that string theorists were able to actually predict all these numbers, not just for lines and conics, but higher homology classes, bigger homology classes also. Okay, so the other little piece of history I want to mention is that in order to talk about these mirror pairs, you need constructions. And the key construction, which has really been the gold standard in thinking about mirror symmetry, is due to Batarov, who found, well, literally millions of examples of Calabi-Yau threefolds. Yeah, so just to address Sheldon's comment, of course, you were more present in that discussion than I was, but my impression was that the final number wasn't agreed on until after the Candelas et al. Paper came out. Yeah, so I'm not quite sure how much I should respond to the questions rising in chat, since it could. Dan?
Yeah, I think you can go on. You
Okay.
can let the questions, yeah.
I should take the question. So
No,
question,
you should go on, and
okay.
we'll deal with the questions later, yeah.
Okay, yeah. So I will get back to those questions, but getting worried that it might just be a little bit too many interruptions. Anyway, it's a good question. So Batarov constructed mirror pairs can be constructed from, or constructed as hypersurfaces in toric varieties. And at the level of Calabi-Yau threefolds, there are approximately 400 million such hypersurfaces. So this provides a huge range of examples, and essentially all the work that's been done in mirror symmetry since has more or less made use of the better of construction. But nevertheless, that leaves the question, is there some general way of constructing mirrors? And I should say this work is 1992, I think, is when the preprint came out. And since then, that's left open this question as to whether one can find a general construction for mirrors. And what I propose is that the answer is yes, and that's what my work with Siebert is about. Okay, so maybe that's a good place to pause for questions. That's the introduction.
There was a question about the number of curves is an integer,
Yes.
but the periods are
Yeah,
transcendental.
so to answer that question, I'm of course being extremely vague here. In fact, what one has to do is look at a whole family of mirrors. You can let the complex structure on the mirror vary. And then the period integrals become functions on the moduli, complex moduli space of the mirror. And then you have some very delicate thing where you try to expand certain functions or certain periods in certain coordinates determined by other periods. And that leads to a rather complicated description, a complicated recipe, but does eventually get a generating function, a power series whose coefficients are the integers we're actually looking for.
You can go ahead.
Yeah, and I think for the question about Gromov-Witten invariants, that's perhaps beyond the scope of this talk, so I'll put that one aside. Okay, so yeah, so let's go on then. So the context I'm going to work on looks a little bit different. So our context is we fix a log Calabi-Yau manifold. Now, what is this? This is a pair XD, where X is a non-singular variety, and D contained in X is a normal crossings divisor. With, it should be anti-canonical, so with Kx plus D equal to 0. So roughly speaking, what this is saying, roughly, or maybe precisely, I don't think I need to say, sorry, that's not the eraser. There's the eraser. So in other words, there exists a nowhere vanishing holomorphic form, a top-dimensional holomorphic form on X minus D with simple poles. So it will blow up along D with simple poles along D. Okay, so this is a slight variant of what I said before, where I defined the Calabi-Yau manifold as a complex manifold with a nowhere vanishing holomorphic form. Here I'm allowing some poles. Now, the one special case, well, an additional case, so in general, we will either consider the case that X is compact, or the case that X appears is total space of family. So X over some one-dimensional germ of a curve with the special point in there and a fiber X0 sitting inside there. And we take D to be equal to the fiber X0. So these are the two cases, and I want this map pi should be proper, so the fiber should be compact. Okay, so it's either we just have an individual object, X, or we should think of X as really being a family of objects with the fibers of pi here, in this case, here. The fibers of pi are actual Calabi-Yau manifolds. So those of you who are old hands at mirror symmetry will recognize that in dealing with mirror symmetry for Calabi-Yaus, you always want to consider a given degeneration of a Calabi-Yau eventually will impose the maximally unipotent condition on that family. But for the bulk of the talk, I think it's simply easier, it's technically easier to discuss, to just consider the case where X is compact. And I'll just say a few words about the second case at the end of the talk. Okay, so let's now write D write D as a sum of its irreducible components. So we have a bunch of components. And are the irreducible decomposition of D. And I want to build from here, we will build the dual complex of D. So this is going to be a combinatorial object which encodes how the various irreducible components of D intersect or interact. So let's first, just again to make this discussion relatively simple, let's assume that for any index set subset of 1 through S, DI, which is defined to be the intersection of all of the components indexed by elements of I, assume that this D sub I is connected. So this kind of example you should have in mind as a very simple example is P2 with 3 lines. This is good, and an example that's not so good because it violates this condition is P2 with a line plus a conic, because the intersection of the line and the conic consists of 2 points, which is not connected. As I say, this is just allows simplicity of exposition. Okay, so now from this, we will build the dual complex of D as a cone complex in the vector space, or the R vector space, with basis D1 through DS. And in particular, I'll define, let me define P. This will be a collection of cones. It will be the cone generated by the DIs for I and I, so sum R greater or equal to 0, DI, whenever the corresponding So capital I ranges over subsets of the index set 1 through S, and we only allow those I for which di is actually non-empty. So the intersection of those d little I contained in the index set I should be non-empty. And then we let B be just the union of all these cones. Okay, so this is a purely combinatorial object. Maybe I should just pause before I go to the next page, because unlike a regular talk where you can roll the blackboard up and let people continue to see this, maybe here you need a bit of time to absorb that. So I think this is best illustrated with PI. Where should a PI be, Dave? So sigma is an element. This may not be legible. Let me try to. Right there. So I just take the union of all the elements of sigma, so of P. Sorry. So Dave, I'm a bit confused by what you mean by PI. Oh, no, we're ranging, sorry, Dave. Okay, maybe this is not so clear. I'm ranging over all subsets of capital I. Let me do an example. I think that will clarify things. So here is one of the, is an example I want to keep running throughout the talk. So I'm going to start by taking P1 cross P1. And I will take its toric boundary. In other words, I will take as the boundary D is 0 cross P1 union infinity cross P1 union P1 cross 0 union P1 cross infinity. So that looks something like this. That's D and sitting inside P1 cross P1. Now I will then blow up. I will choose some point, say over here, blow up a point. Let me call this D bar. Let's blow up a point in say 0 cross P1 and let X, well, let X be the blow up and D the strict transform of D bar. So the picture is I have a blow up here. I still have D, which is isomorphic to D bar, but now there's an exceptional curve, which is sitting here, which is mapping down to the point we blew up. So it's a very slight modification to P1 cross P1. Now, let me label these pieces of D, D1, D2, D3, D4. And now what the P looks like, well, we have one two-dimensional cone for every index set of size 2 for which the boundary divisors, the DIs in that index set have non-empty intersections. Sorry, that was a rather long-winded sentence. So let me just draw this. Picture is always better. So the picture of the dual complex, it's a union of 4 cones. The generators of the one-dimensional cones are D1, D2, D3, D4. I don't have a cone that contains both D1 and D3 because D1 and D3 are disjoint. And I don't have a cone containing D2 and D4 because, again, D2 and D4 are disjoint. But I do have one-dimensional cones corresponding to each of the boundary divisors and I have two-dimensional cones corresponding to the intersection points of the divisors. And of course, I have a zero-dimensional cone, namely the origin corresponding to the empty set of divisors. Okay, so I hope that that clarifies things. So this is B, and P is just the collection of all of these cones. So P is a collection of cones. And I'm happy to say I've made Dave happy. Okay, so it's just a combinatorial gadget, which, so yeah, so Andy asks whether this is what you get before blowing up or after, and thanks for asking that question, because you get the same picture before or after. Now, if you're a toric geometer, you'll say, well, actually, this looks like the fan for P1 cross P1. And indeed, the fan for P1 cross P1 will capture the same combinatorics. However, you should bear in mind that this is really a piecewise linear object. This is sitting inside a four-dimensional vector space spanned by D1 through D4. It's not actually sitting in the planes. It's not naturally a copy of R2. Okay, so any questions at this point? Any further questions? Just pause.
No, I think you're good.
Okay. Yes, I ignore linear equivalence relations. So I have a question about why these are called log Calabi-Yaus, and the reason is that the homomorphic form has logarithmic poles, can be viewed as having logarithmic poles along the boundary. Okay, so now a new piece of notation. Let's define, so we've just defined B as being this piecewise linear gadget. Let's define B of Z to be the set of all summation AI DI in B such that the AIs are integers. Okay, so these are all the points in B with integer coordinates. Now, here's the key point as to why I'm interested in this set. So points of B of Z record tangency orders for stable map. So I haven't actually used the word stable map, so for maybe I should say holomorphic maps of curves F from C into X. So typically one is interested in these kind of enumerative curve camping problems when it's interested in pointed curves. So typical question, consider maps from pointed curves. So that's just a curve with some collection of distinct points in X, X1 through Xn, in C distinct points. And we wish to impose tangency of F at the divisor di to be at X, or at a point xi, with the divisor dj. Okay, so we'd like some language for saying that this curve is tangent to the divisor di at the point xi. And how do we do this? Well, let's think about that a little bit. Let's say that X looks something like this, and we have our curve with some marked points, and its image might, for example, do something like this. So this is meant to be tangent here. So we were supposed to have 3 points. Let me write the points there in red. So those 3 points map to these 3 points. And again, using the notation I was using earlier, this is D1, D2, D3, D4, X1, X2, X3. This might be X1, X2, X3. So being tangent, or F being tangent to dj at xi to order A means the following. What you do is you take a local equation, a local defining equation, for dj near f of xi, say tj equals 0. And then if you compose that with f, you get a function. Sorry, that's going the right way. Tj composed with f is now a function defined in a neighborhood of xi. And in particular, it has some order of vanishing. And being tangent to order A means that order vanishing should be A. Okay, so for example, here, if I point back to this picture, does the pointer show up?
Yes.
Good, okay. If I point to this picture, so you see at this point, the curve only meets D1, and the way I've drawn this, the curve is transversal to D1. If I pull back the local equation for D1, I'll get a function on the curve at x1, in a neighborhood of x1, which vanishes just to order 1. And this point doesn't land in any of the other divisors, so we don't have any condition on the local equations of the other divisors. At the point x2, I have 2 divisors the point maps into, and I can pull back the 2 equations of those 2 divisors, and I can find, according to this picture, that we are transversal, so contact order 1 with D1, and we're simply tangent with D2. So that's sort of tangency, what I call tangency order 2 in this language. And this point here looks like it's transverse to D3 and D4. So the point is I can encode this information. So a point summation AI DI, let me use J here, encodes in B of Z, encodes such a tangency condition. Right, so in other words, it tells us, the condition is, i.e., we should be tangent to dj to order aj. Okay, so for example, over here, using a different color, this tangency condition would just correspond to D1. in B of Z, just demanding that our curve be transversal to D1 and not go through any of the other divisors. This point here corresponds to tangency condition D1 plus 2D2, again, recording the fact that we actually are genuinely tangent to D2. And then this point here would have tangency order D1 plus D2. So this is just a way of encoding tangency conditions of curves with this complicated divisor. Okay. Yes, thanks, Dave. Okay, any other questions before I move on?
You're good, I think.
Okay, yeah. Okay. Right, so now is going to come the punchline. So now we're going to make one more assumption. The real dimension of this polytool cone complex so there's a question from Greg I should answer. So one way to think about this is if you have a pointed curve mapping to X, then so each marked point will give you an element of B of Z, given its tangency conditions. But typically what we're going to do is we're going to impose some set of tangency conditions and then look at the moduli space of all curves satisfying those tangency conditions. Okay, so now let's assume, again, this is not necessary for most of what I'm going to say, but let's assume that the dimension of B is the same as the dimension of X. The real dimension of B and the complex dimension of X are the same. So that was the case in the examples I've given you. Are all divisors non-singular? All the DIs are non-singular. D, of course, is a union of DIs is singular. But so the point is it's normal crossing, so the singularities are very controlled. Okay, so this is in the relative case, in the case where we have X to S with Calabi-Yau fibers. This is actually the maximally unipotent condition. So this is more generally in the log Calabi-Yau case, this is the analog of a maximally unipotent condition. And this is what's the case in which we actually be able to construct the mirror. So what we're actually going to do is we will construct a ring, which I'm going to call R, which is either the affine or a projective coordinate ring. In the two cases, so the log Calabi-Yau or this relative X to S case. Of the mirror. Okay, so I need a little bit more extra data in defining this. So what I'm going to do is, first of all, fix some monoid P, so our semi-group set closed under addition with 0 P containing H2 of X, Z, with the property that P contains the class of every effective curve So every curve that's actually realized by, say, a homomorphic, as every curve class, every element of H2 which is realized as the image of a fundamental class of a curve mapping into X of a homomorphic curve. So I want, first of all, P contains every curve class, so P should be a monoid. So P closed under addition, 0 should be in P, and actually more precisely, P intersect minus P should just be the torsion part of H2, in case there happens to be some torsion H lower 2. Usually that doesn't happen, and then I just demand that the only invertible element, the only element of P whose negation is also in P is 0. Okay, so this is a bit of auxiliary data. And I can then define the monoid ring. So I believe I can work over the, well, let's continue to work over some field, K bracket P. This is the monoid ring of P. That's the direct sum over all P and P of K times Z to the P. So the vector space with basis elements of P and with the usual law for multiplication, Z to the P times Z to the P prime and Z to the, sorry, I just forgot. I not looking at my notes. This should be, I'm going to use the convention that this is T. T to the P times T to the P prime is T to the P plus P prime. Let's call this ring A. And now if I further take a monomial ideal, I contained in A, such that it's an ideal generated by these kinds of gadgets, such that A sub I, which I define to be A mod I, is Artinian, so in particular this some finite dimensional algebra, K algebra. Now, the construction I'm going to give you, so we'll construct an AI algebra, Ri, giving a family, in the two cases, giving a family either spec Ri over spec AI or proj Ri over spec AI. Now, you should view this as going to be the mirror family. Again, for those of you who are sufficiently familiar with the old stories of mirror symmetry, will recognize that this is really, that this scheme is really some infinitesimal neighborhood of the large Kähler limit. I apparently can't spell infinitesimal. Okay, now, if you don't like to work infinitesimally, then there are a couple of things you can do. You can do this construction for all such I and get a formal object, or if you're working over in the projective case, in the second case, you can actually work over spec of the completion of A. But that's largely, that's a straightforward point. It's not particularly relevant. But the main point is that the mirror we get is really a family, and is a family in essentially in a formal neighborhood of the large Kähler limit of the original X. So taking limit over all I will give mirror construction in a formal neighborhood. Of the large Kähler limit. Okay, so that's the basic thing. If I just go back to the previous slide. The basic goal then is to actually construct this ring, and once we've constructed that, we'll be done. And believe it or not, I can actually do that in the remaining 10 minutes of the talk. For those of you who are anxious, I have not actually gotten very far yet. Okay, so construction of Ri. So first of all, I'll write down what Ri is. It's the direct sum over all P in R set B of Z of AI times a symbol, which I'm going to call theta P, and this is what we call a theta function. And the analogy, the reason why we call these theta functions is that if we apply our construction in the particular case of the abelian varieties, we get classical theta functions out of this. Classical theta functions in the mirror. Okay, so this is a free AI module. So far, as it's completely trivial. It's a free AI module whose basis elements are these points of B of Z, which, as I said, is really just capturing tangency conditions for curves. Okay, so far it doesn't look like we've really done anything, and the real magic is going to occur in the definition of the multiplication law. Right? I need an algebra. It's not enough to just have a module over AI. So we need to define theta P times theta Q. And what should that be? Well, that should be a sum of basis elements, sum over R in B of Z, of some structure coefficient, we'll write as alpha PQR, times theta R, where the alpha PQR live in our ground ring AI. So all I have to do is try to define these alpha PQRs. Now let me remind you, AI is K bracket P mod I. So that does allow me to write alpha PQR further as a polynomial in these monomials T to the P. So write that as a sum over P in P minus I of NP, actually, sorry, I didn't mean to use P, beta, N beta PQR times T to the beta, where N beta PQR will in fact be a rational number, which I'm going to assume is contained in the set of rational numbers is contained in our field. In other words, I'm assuming we're in characteristic 0. Okay, so far I haven't said anything at all. I've just said this is what we need to do to find a product. And of course, the real mystery, the real trick is how we define these numbers N beta PQR. I've just reached my allowable limit of whiteboards. So I'm going to save these. I will later email them to the organizers so they can be distributed. But let me pause in case I need to point to something on these slides. Let me pause and ask again if there are any questions.
I don't see any.
Okay. So I will briefly stop sharing, and then I will go back to sharing, and now I should have a clean set of whiteboards. Much more efficient than erasing a blackboard. Okay, so definition. So of the numbers n beta PQR. So the first thing to observe is that let's take a look at the point R. So R is in B of Z. So that can be written as R is equal to summation AI di, where I ranges over some index set with all the AIs positive. And in particular, this index set, so namely the set of indices for which the coefficient of di is positive, that index set determines a intersection of di's. So this determines di, and I will fix a point z in di. So now let's let n beta PQR be the number of maps C x1, x2, x out to x with C, first of all, rational, so genus 0, with, this map is F, the Push-Farter fundamental class of the curve C is beta. So in other words, this curve represents the class beta. So next we have some tangency conditions. So we have the tangency condition at x1 sorry, Salman, Z is a point in this divisor, so it's a point of the variety. So the tangency condition at x1 is given by P. The tangency condition at x2 is given by Q, and finally the tangency condition at x out is given by, now here's a little bit of a mystery, minus R, and f of x out is equal to Z. Now, at this point, if you've followed me so far, you should be asking, what the hell does a negative order of tangency mean? And the answer is, we have developed a theory which makes sense of that. So I'll say a bit on the next slide about that. Let me just point out here, so we have these tangency conditions make sense. The condition, that's not so helpful, tangency condition. So we're constraining where the output point goes to. That's why we chose this point. We chose this point inside di to constrain where the output point goes. That gets us down to a zero-dimensional problem. Now, the issue, and I think I'm going to address Greg's question here, is that if you have a negative order of tangency, you have a holomorphic map. So imagine, again, let's draw a simpler situation here. So we have the divisor D. Of course, if we have an equation, if we have a curve, and we pull back a local equation sorry, that's the wrong color. We pull back a local equation for the divisor to the curve, that local equation is always going to have a zero. It's not going to have a pull. So in order to encode these negative orders of tangency, one actually has to do something quite subtle and to define negative orders of tangency. one uses logarithmic geometry, which would be an entirely different talk, and defines something we call punctured invariants. And this is joint work with Dan Abramovich, Chen, myself, and Siebert. So this is quite a long story. Essentially, curves with negative order of tangency, I will use a different color to exhibit one with negative order of tangency, more or less need to fall into the divisor. And once it falls into the divisor, there's no real sense you can make of directly of what it means for the pullback of the equation to have a zero pole at a given point, because the function vanishes entirely on the curve. So there's no order of zero pole at a given point. But essentially, there's a way of adding some extra data, of enriching the structure of the curve in order to assign sort of all of the tangency of this curve, all the intersection number of this curve with the divisor to a given point. And if that intersection number happens to be negative, we can do it in such a way that we get negative order of tangency. So that is admittedly very vague, but that would be an entirely different talk. But let me now state the main theorem. The main theorem is that with this, well, maybe I should say, these numbers can be defined rigorously. I think the answer to Michael's question is, I don't think so. And with this product, Ri is an associative commutative algebra with a unit, which is in fact theta 0. Okay, so I'm out of time. So normally I would spend a bit more time doing the example I introduced earlier. This of course does not prove that what we have really done is constructed the mirrors, and those of you who haven't followed recent developments might indeed wonder why that's the case. There's still work to be done, but many years of experience suggest that this really is going to give the mirror. So maybe I should end there and take questions.
All right. Well, thank you, Mark.
And I see questions accumulating.
So if someone wants to ask a question, you can raise your hand, and then using the participants panel, I think.
Yeah, so we have a number of questions already on the chat, so perhaps I should address those first.
Well, here's someone.
Someone's raising their hand.
Yeah, go ahead. Sorry, I can't pronounce. Sheriar, go ahead.
Yeah, Sheriar, thank you so much, Sheriar.
Yeah.
I just have a question. Is there any hope of defining mirror symmetry over algebraic number fields rather than the complex numbers? That is, you start off with x over q, and your x check is also defined over q, or an algebraic extension of that, and that the acting on the cohomologies match. I mean, not just that the field of definitions are algebraic, but somehow the Frobenius and the arithmetic of the two sides also match with each other.
Right. So all I can say about that is that our construction for the mirror is defined over Q.
Yes,
because those numbers were indeed rational numbers. There has been no, I still don't feel there's been any serious arithmetic insights in mirror symmetry, and I think those are very interesting questions. But it does, because our setting does really work over Q, it's reasonable to try to ask these questions, but I don't know the answers.
Okay.
Yeah, I don't see any other hands raised, but we could read some of the questions. So
yeah,
Albert
okay,
Schwartz. Yeah, maybe we should repeat the question though.
Yeah, so the question from Albert Schwartz is, can one formulate these theories in terms of n equal to SUSY models, in terms of A and B models? So I don't have the really the physics terminology to go with this, but what I can say is that the pair XD we're starting with, you should really think of it as being the A model, because we're doing Gromov-Witten theory on that. So this curve counting is Gromov-Witten theory. Ostensibly, it should just have to do with the symplectic structure of the starting gadget XD, and then we construct the B model. But other than those slogans, there isn't really anything I know how to add in terms of the physics.
Okay, so Marco Castronovo has a question.
Yeah, okay, that's also a good question.
He's on,
indeed, this
he can ask it. Go ahead.
yeah. So I assume that X was smooth and D was normal crossings. Let's see, Marco's going to come up, or
yeah, I wanted to ask if this construction also works for log smooth X.
Yeah, indeed it does. It's the whole logarithmic Gromov-Witten theory, punctured Gromov-Witten theory works in the log smooth setting, and so everything I said goes through. It's just much easier to exposit it in this sort of normal crossings case.
Okay, Irit has a question. Go ahead. Irit? Okay, maybe we should go to one of the other questions from the chat. Go ahead.
Okay, so then the next one from Kai. So at the moment, so Kai is asking, would this construction of the mirror imply one can reconstruct all higher genus Gromov-Witten invariants from these genus zero Gromov-Witten invariants with tangential conditions? So of course, at the moment, I'm making no claims about what we can actually prove about mirror symmetry. One of the first goals in the near future is to try to prove genus zero mirror symmetry, namely that we can use the mirror in the traditional way to calculate the genus zero Gromov-Witten theory of what we started with. Now that shouldn't be a hugely surprising result because we've used the genus zero Gromov-Witten theory to construct it. So that should in some sense, make genus zero Gromov-Witten theory fairly transparent. It works because it's built into the construction. For higher genus, there's still a lot yet poorly understood about the general higher genus B model, and there are many interesting questions there, and I don't want to make any predictions.
Okay, Greg Moore had a question. Can you see that, Mark?
Yeah, are the ends rational because you divide by an order of an automorphism group? That's right. So Gromov-Witten invariants always tend to be rational numbers because we generally we're looking at Deligne-Mumford stack rather than the moduli space, but a Deligne-Mumford stack rather than a scheme.
Alani has a question. Whether the tangency numbers can be positive in some directions and negative in others.
Yeah, so the general theory of punctured invariance allows, sorry, I didn't actually see the question there, but
well, that's okay.
But if I take what, oh, there it is. Okay, right, sorry. Yeah, so in general, we allow quite general contact orders. So in the general theory of punctured invariance, we can allow both positive with some divisors, negative with some other. But there are some interesting phenomena, which is that even in an unobstructed situation, so this is an answer very specifically for a more sophisticated Gromov-Witten audience. Even in an unobstructed situation, the moduli space might not be equidimensional. You have different dimension components depending on what the combinatorics of the curve is and how it interacts with the boundary. So frequently actually getting an actual number out of punctured invariance or punctured maps is quite subtle, and it takes some experience getting used to that.
Andy Knightsky has a question. Go ahead, Andy.
Yeah, how computable are these numbers?
Yeah, so in many simple cases, they seem to be quite computable, in the sense that usually you only have to do a few calculations to figure out that you've gotten all of the relations. The example I was going to do with P1 cross P1 blown up at one point. Okay, that's sort of the simplest non-trivial example, but there's really just a couple of curves you have to count. But you know, we're slowly gaining experience on how to actually do these calculations, and I think as time goes on, hopefully many of these things can be done on a computer at some point.
Arpan Saha has a question. How does one interpret this construction in terms of the SYZ fibration?
Right. Yeah. So one can consider this gadget B that we built can be considered as the base of the SYZ fibration in some crude sort of non-Archimedean terms. And of course, this whole story was very much inspired by the SYZ picture over the last 20, 25 years. However, we don't actually make use of any explicit fibration in this story.
Okay, Salman Akbalat has another question. When divisors, sorry.
Yeah, so of course, when we're dealing with a normal crossings divisor, we can't resolve the singularities. If you blow up one of the singular points, you get a new exceptional divisor, but there's still new singular points where that exceptional divisor meets the old bit of the divisor. So if I just draw a picture of that, so we start with, say, a divisor that looks like that. If we blow up this point, we then get a new exceptional divisor that looks like that. And of course, we haven't gotten rid of the singularity. We've simply replaced it with two singularities. So generally speaking, once we get to normal crossings, there's nothing more we can do. We're stuck with that.
Jim Bryan asks whether you recover the Batira-Borisov mirror construction.
So we fully expect it to. The reason being that this construction is very closely related to the old construction that Bernd and I had of mirrors from dating back to about 2007. It hasn't been proved to be equivalent, but we have every expectation it's equivalent. And that construction has been proved to recover the Batira-Borisov construction. So there is still some work to be done, but we believe it can be done. And some people are actively working on that question.
Okay, Greg Moore wants to know if there's an analog of Gopakumar-Vafa, I presume.
Short answer, I don't know. No.
Okay. Let's see. And Irit's question was, can you reconstruct the log or punctured GW invariants from ordinary Gromov-Witten invariants?
I think that's difficult. At the moment, we don't understand punctured invariants well enough to expect that to be the case.
Okay. And Maxim Kontsevich has a question.
Yeah, no, I just have a I have just a small comment that, you know, of course, this work by Tony Yu and Sean Keel, when you have when this is open torus sitting in this open part, then the all numbers will be positive and integer. In fact, it will be degrees of certain. Yeah, just notice it.
Yeah, so I think the so essentially the way things work, the reason why that works in Tony and Sean's case is that the numbers are completely enumerative in that situation. So in other words, actually you're counting a finite number of curves with no automorphism groups. And so you never have to do anything virtual. And it seems that at the moment you leave the realm of their assumptions, you might, for example, at least get negative numbers. I think integrality might still be true, but I don't know how to prove that. But I know positivity fails.
All right, so I think that takes care of all the questions. So again, thanks to Mark.
There's still a raised hand, but.
No, we got her question, I think. She asked about the log GW.
Ah, right. Okay.
So again, thanks to Mark. And the next lecture in this series will be next week. So notice the schedule change due to Memorial Day, such as it is in the US. And the next speaker is Miranda Chang, and her title is Quantum Modularity from 3 Manifolds. So I refer you to the website for the complete schedule. Thanks.